Section 1 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. Corbin. Digging with Dynamite. Most people are afraid of the word explosion and shudder with apprehension at the mention of dynamite. The latter particularly conjures up visions of anarchists, bombs, and all manner of wickedness. And yet the time seems to be coming when every farmer will regard explosives of the general type known to the public as dynamite as among his most trusty implements. It is so already in some places. In the United States, explosives have been used for years, owing to the exertions of the DuPont Powder Company, while Messrs. Curtis and Harvey and Messrs. Nobels, the great explosive manufacturers, are busy introducing them in Great Britain. It will perhaps be interesting first of all to see what this terror-striking compound is. One essential feature is the harmless gas which constitutes the bulk of our atmosphere, nitrogen. Ordinarily one of the most lazy, inactive, inert of substances, this gas will, under certain circumstances, enter into combination with others, and when it does so, it becomes in some cases the very reverse of its usual peaceful, lethargic self. It's as if it entered reluctantly into these compounds, and so introduced an element of instability into them. It's like a dissatisfied partner in a business, ready to break up the whole combination on very slight provocation. And it must be remembered that an explosive is simply some chemical compound which can change suddenly into something else of much larger volume. Water, when boiled, increases to about 1,600 times its own volume of steam. And if it were possible to bring about the change suddenly, water would be a fairly powerful explosive. Coal burned in a fire changes, with oxygen from the atmosphere, into carbonic acid gas, and the volume of that latter which is so produced is much more than that of the combined volumes of the oxygen and coal. When the burning takes place in a grate or furnace, we see nothing at all like an explosion, for the simple reason that the change takes place gradually. That is necessarily so, since the coal and oxygen are only in contact at the surface of the former. But if, however, we grind the coal to a very fine powder and mix it well with air, then each fine particle is in contact with oxygen and can burn instantly. Hence, coal dust in air is an explosive. It used to be thought that colliery accidents were due entirely to the explosion of methane, a gas which is given off by the coal. But it has of recent years dawned upon people that it is the coal dust in the mine which really does the damage. The explosion of methane stirs up the dust, which then explodes. The former is comparatively harmless, but it acts as the trigger or detonator which lets loose the force pent up in the innocent-looking coal dust. Hence the greatest efforts in modern collieries are bent towards ridding the workings of dust, or else damping it, or in some other way preventing it from being stirred up into the dangerous state. So the essential feature of any explosive is oxygen and something which will burn with it. If it be a solid or liquid, the oxygen must be a part of the combination or mixture, for it cannot get air from the surrounding atmosphere quickly enough to explode. And moreover, it is generally necessary that explosives should work in a confined space, away from all contact with air. So oxygen, of necessity, must be an integral part of the stuff itself. But when oxygen combines with anything, it usually clings rather tenaciously to its place in the compound and is not easily disturbed quickly. That is where the nitrogen seems to find its part. It supplies the disturbing element in what would otherwise be a harmonious combination, so that the oxygen and the burnable substances readily split up and form a new combination with the nitrogen left out. Of all the harmless things in the world, one would think that the sweet, sticky fluid, glycerin, which most of us have used at one time or another to lubricate a sore throat, was the most harmless. As it stands in its bottle upon the domestic medicine shelf, who would suspect that it is the basis of such a thing as dynamite? Such is the case, however, for glycerin, on being brought into contact with a mixture of sulfuric and nitric acids, gives birth to nitroglycerin, an explosive of such sensitivity, of such a furious, violent nature, that it is never allowed to remain long in its primitive condition, but it is as quickly as possible changed into something less excitable. Glycerin is one of those organic compounds which is obtained from once living matter. Arising as a by-product in the manufacture of soap, it consists, as do many of the organic substances, of carbon and hydrogen, the atoms of which are peculiarly arranged to form the glycerin molecule. To this the nitric acid adds oxygen and nitrogen, the sulfuric acid simply standing by, as it were, and removing the surplus water which arises during the process. So while glycerin is carbon and hydrogen, nitroglycerin is carbon, hydrogen, nitrogen, and oxygen. In this state they form a compact liquid which occupies little space. The least thing upsets them, however. The carbon combines with oxygen into carbon dioxide, commonly called carbonic acid gas. The hydrogen and some more oxygen form steam, while the nitrogen is left out in the cold, so to speak, and the total volume of the gases so produced is about 6,000 times that of the original liquid. It is easy to see that a substance which is liable suddenly to increase its volume by 6,000 times is an explosive of no mean order. But the fact that it is liable to make this change on a comparatively slight increase in temperature or after a concussion makes it too dangerous for practical use. It needs to be tamed down somewhat. Well, this was first done by the famous Nobel, who mixed it with a fine earth known as kieselguhr, whereby its sensitiveness was much decreased. This mixture is dynamite. It will be seen that the function of the earth is simply to act as an absorbent of the liquid nitroglycerin, and several other things can be used for the same purpose. Moreover, there are now many explosives of the dynamite nature, but differing from it in having an active instead of a passive absorbent, so that the decrease in sensitivity is accompanied by an increase in strength. For example, gelignite, which is being used for agricultural purposes in Great Britain, consists of nitroglycerin mixed with nitrocotton, wood meal, and saltpeter. The wood meal acts as the absorbent instead of the kieselguhr, while the nitrocotton is another kind of explosive, and the saltpeter, one of the ingredients in the old gunpowder, provides the necessary oxygen for burning up the wood meal. Nitrocotton is made in much the same way as nitroglycerin, except that cotton takes the place of the glycerin. Cotton is almost pure cellulose, another organic substance, like glycerin insomuch as it is composed of carbon and hydrogen, but unlike it, containing also oxygen. Treated with nitric acid, it also forms a combination of carbon, hydrogen, oxygen, and nitrogen, which is called nitrocotton, nitrocellulose, or gun cotton. It may be asked, why, if these two substances are thus similar, need they be mixed? The answer is that although alike to a certain degree, they are not exactly the same, and the modern manufacturer of explosives, in his strife after perfection, finds that for certain purposes one is the best, and for others another, while for others again a combination may excel any single one. For some work another kind of explosive altogether is to be preferred. This is based upon chlorate of potash, a compound very rich in oxygen, which it is prepared to give up readily to burn any other suitable element which may be at hand. A well-known explosive of this class is that known as shedite, since it was first made at a factory at Shed in Savoy. For the sake of simplicity, however, I propose in the following descriptions to refer to all these explosives under the common term dynamite, since that will probably convey to the general public an idea of their nature better than any other term or terms which I could choose. So now we come to the great question: how can the modern farmer benefit by the use of high explosives such as these? The answer is in many ways. Let us take the most obvious one first. A farmer has been plowing his land and growing his crops upon it for years. Perchance his forefathers have been doing the same for generations. Every year for centuries possibly, a hard steel plowshare has gone over that ground, turning over and over the topsoil to a depth of 6 to 8 inches. Each season the plants, whatever they may be, grow mainly in that top layer. They take the goodness or nourishment out of it, and eventually becomes more or less sterile. By properly rotating his crops, he mitigates this to a certain extent. In addition to which he restores to the land some of its old nitrogenous constituents by the addition of manure. Yet do what he will, this thin top layer is bound to become exhausted, and all the while a few inches lower down there is almost virgin soil, which has scarcely been disturbed since the creation of the world. Nay, more, that virgin soil, with all its plant food still in it, is not only doing little for its owner, it is positively doing him harm. For every time his plow goes over it, it tends to ram it down flat. Every time a man walks over it, the result is the same. Every horse that passes, everything that happens or has happened for centuries in that field, tends to make that soil just below the reach of the plowshare a hard, impervious mass, through which only the roots of the most strongly growing plants can find a way, and which tends to make the soil above it wet in wet weather and dry in dry weather. Thus roots have to spread sideways instead of downwards, or growing downwards with difficulty. Each plant has to expend vital energy in forcing its roots through the hard ground, which it might better employ in producing flowers or fruits. And there is no natural storage of water. A shower drenches the ground. In time it dries through evaporation into the air, and then when the drought comes, all is as arid as the Sahara. That hard subsoil is known by the term hardpan, and as we have seen, it is produced more or less by all that goes on in the field. Even worse is the case, a very frequent one too, wherein there is a natural stratum of clay or equally dense waterproof material lying a few feet down. Beyond the reach of any plow, this hard stratum can be broken up by the use of dynamite. The usual method is to drive holes in the ground about 15 to 20 feet apart and about 3 or 4 feet deep, right into the heart of the hard layer. At the bottom of each hole is placed a cartridge of dynamite with a fuse and a detonator. This latter is a small tube containing a small quantity of explosive which, unlike the dynamite, can be easily fired and initiates the detonation of the cartridge. When these miniature earthquakes have taken place all over a field, a very different state of things prevails. The hardpan has been broken. The explosive used for such purpose has a sudden shattering power, whereby it pulverizes the ground in its vicinity rather than making a great upheaval at the surface. The sudden shock makes cracks and fissures in all directions through which roots can easily make their way. Moreover, it permits air to find an entrance, thereby aerating the soil in such a way as to increase its fertility. The heat, or else the chemical products of the explosion, seem to destroy the fungus germs in the ground. And finally, a natural storage of water is set up. Heavy rain, instead of drenching the upper soil, simply moistens it nicely, while the surplus water descends into the newly disturbed layers, there to remain until the roots pump it up in time of drought. It is stated that an acre of hay pumps up out of the soil 500 tons of water per annum, and so it is easy to see what an important feature this natural water storage is. Farmers say that their crops have doubled in value after thus dynamiting the subsoil. This operation has been spoken of as a substitute for plowing, but that may be put down to journalistic license, for while it truly conveys the general idea, it is hardly correct. The ordinary plow turns over about 8 inches. The special subsoil plow reaches down to about 18 inches. But the dynamite method loosens the ground to a depth of 6 or 7 feet. Corn roots, if given a chance, will go downwards from 4 to 8 feet. Potatoes go down 3 feet. Hops 8 to 18 feet, and vines 20 feet. So it is easy to see how restricted the plants are when their natural rooting instincts are restrained by a hard layer at a depth of 18 inches or so. The holes are made by means of a bar or drill. A great deal depends, of course, upon the hardness of the soil. Sometimes a steel bar has to be driven in by a sledgehammer. At others, a pointed bar can be pushed down by hand. In some cases, it will be found that the best tool to employ is a dirt auger, a tool like a carpenter's auger, which on being turned round and round bores its way into the earth. However it may be done, one or more cartridges of dynamite are lowered into the finished hole, one of them being fitted with the necessary detonator and fuse. Then a little loose earth or sand is dropped into the hole until it is filled to a depth of 6 inches or so above the uppermost cartridge. Above that, it is quite safe to fill the hole with earth, ramming it in with a wooden rammer. This is called tamping, and it is necessary in order to prevent the force of the explosion being wasted in simply blowing up the hole. What is wanted is that the explosion shall take place within an enclosed chamber, so that its effect may be felt equally in all directions. The holes are generally about 1.5 inches or 1.75 inches in diameter. There are 2 ways of firing the charges. One is by means of fuses. The detonator is fastened to one cartridge, and a length of fuse is attached to the detonator, which, passing up the hole, terminates above the ground. The fuse is a tube of cotton filled with gunpowder, and it burns at the rate of about 2 feet a minute. And thus, if 3 feet of fuse be used, the man who lights it has 1.5 minutes in which to find a place of safety from falling stones. The other way is by electricity. In this case, an electric fuse is attached to the cartridge, and 2 wires are led up the hole. These are connected to an electrical machine, which causes a current to pass down into the fuse, where, by heating a fine platinum wire, it fires the detonating material with which it is packed. This detonating material, in turn, fires the dynamite. The advantage of the electrical method is that 20 or 30 holes being simultaneously connected to the same machine can all be fired at once. And now let us think of another kind of farming in which fruit trees are concerned. With a large tree, the need of plenty of underground space for its roots would seem to be more important even than that in the case of annual plants like wheat. And yet we know very well that the usual procedure is to dig a small hole just about big enough to accommodate the roots of the sapling when it is planted, while the ground all round is left undisturbed. The assumption is that the tree will in time be able to push its roots through anything which is not actually solid rock. So much is this the case that one authority has thought fit to warn tree growers in this picturesque fashion. When planting a tree, he says, forget what it is you're doing and think that you're about to bury the biggest horse you know. How many people, when planting any tree, dig a hole big enough to bury a horse? It is fairly safe to reply, only those who do it by dynamite. The method of working is to bore a hole nearly as deep as the hole you want to blast. At the bottom, place a powerful charge, far stronger than you would use for subsoiling, as just described. That will not only blow a hole big enough for you to put your tree in, but it will loosen the ground all around the hole for yards. The main debris from the hole will fall back into it, but that will not matter much, since, being all loose, it is an easy matter to remove as much as is necessary to plant the young tree. The advantages are the same as those enumerated in the previous case, namely, the loosened ground gives more scope for the roots. Apple tree roots want 20 feet or so. The ground holds moisture better, and the explosion kills the fungus germs. In addition to these, there is the advantage that to blast a hole like this is cheaper than digging it. And that the advantages are not merely theoretical is shown by the fact that trees so planted actually do grow stronger, bigger, and quicker than precisely similar ones under the same conditions, but set in the ordinary way with a spade. And not only do new trees thus benefit, old trees can be helped by dynamite. Many an existing orchard has been improved by exploding dynamite at intervals between the rows of trees. Care has to be taken to see that the disturbance is not so violent or so close as to damage the trees. But that can be easily arranged, and then the result is that the soil all around the trees is loosened. The roots are given more freedom, and the water-storing properties of the ground are greatly improved. Again, how often a farmer is troubled with a pond or a patch of marshy ground right in the midst of his fields. It is of no use, and simply serves to make the field in which it occurs more difficult to plough and to cultivate, besides being so much good land wasted. Now, the reason for the existence of that pond or marsh is that underneath the surface there is an impervious layer in which, as in a basin, the water can collect. Make a hole in that, and it will no more hold water than a cracked jug will, and to make that hole with dynamite is the easiest thing in the world. If the pond be merely a collection of water which occurs in wet weather, but which dries up quickly, there simply needs to be drilled a deep hole and a fairly strong explosion caused at the bottom of it. How deep the hole must be depends upon the formation of the earth at that point, and how low down is the stratum which, being waterproof, causes the water to remain. It is that, of course, which must be broken through, and so the explosion must be caused at a point near the under side of that layer. With a little experience, the operator can judge the position by the feel of the tool with which he makes the hole. If the pond is permanent but shallow, men can wade to about the center, there to drill a hole and fire a shot. If it be permanent and deep, then the work must be done from a raft, which, however, can be easily constructed for the purpose. Once broken through, the water will quickly pass away below the impervious stratum, and useless land will become valuable once more. The same may be done on a larger scale by blasting ditches with dynamite. This is in many cases much cheaper than digging them. A row of holes is put down, or even 2 or 3 rows, according to the width of the proposed ditch. In depth they are made a little less than the depth of the ditch that is to be, and for a reason which will be apparent, they are put very close together, say 3 feet or so apart. Preparations may thus be made for blasting a ditch hundreds of feet long, and then all are fired together. The earth is thrown up by a mighty upheaval, a ditch being produced of remarkable regularity, considering the means by which it is made. The sides, of course, takes a nice slope. The debris is thrown away on both sides and spread to a considerable distance, so that, given favorable conditions and a well-arranged explosion, there is constructed a finished ditch which hardly needs touching with spade or other tool. It not being feasible to fire a lot of holes electrically, the limit being about 30, the simultaneous explosion of perhaps hundreds has to be brought about in some other manner, and usually it is accomplished by the simple device of putting the holes fairly near together and firing one with a fuse. The commotion set up by this one causes the nearest ones to go off, they in turn detonating those farther on, with the result that explosion follows explosion all along the line so rapidly as to be almost instantaneous. A farmer who is troubled by a winding stream passing through his land, cutting it up into awkward shapes, can straighten it by blasting a ditch across a loop in the manner just described. In the case of low-lying land, however, ditches are obviously no use, since water would not flow away along them. In that case, the principle suggested just now for dealing with an inconvenient pond can sometimes be used. Or if the subsoil be blasted through at several points, it is very likely that water will find a way downwards by some means or other. And the list of possible uses is by no means exhausted yet. A man opening up virgin land often finds old tree stumps his greatest bother. He can dig round them and then pull them out with a team of horses, but by far the simpler way is with a few well-placed dynamite cartridges, for they not only throw up the stump for him, but they break it up, shake the earth from it, and leave it ready for him to cart away or to burn. Boulders, too, can be blown to pieces far more easily than one would think. The charges may be put underneath them, as with the tree stumps, but in many cases that is not necessary, all that is needed being some dynamite laid upon the top of the rock and covered with a heap of clay. So sudden is the action of the explosive that its shock will break up the stone underneath it. And yet another way, perhaps the most effective of all, is to drill a hole into the stone and fire a charge inside it. It behooves the onlooker then to keep away, for the fragments may be thrown 300 or 400 feet, a fair proof that the stone will be very thoroughly demolished. Even in the digging of wells, explosives may be useful. In that case the holes are made in a circle, and they slant downwards and inwards, so that their lower ends tend to meet. The result of simultaneously exploding the charges in these holes is to cut out a conical hole a little larger in size than the ring and a little deeper than the point at which the explosion took place. The bottom of that hole can be leveled a little and the operation repeated, and so stage by stage the well will proceed to grow downwards. The thought that naturally occurs to one is this: all the operations described may be very well, the cost may be very low, and the effects good, but are they sufficient to compensate for the risks necessarily dependent upon the use of explosives? The doubt implied is that question, natural though it be, is based upon prejudice, with which we are all more or less afflicted. The art of making these explosive substances has been brought to such a pitch that with reasonable care there is no risk whatever. The greatest possible care is used in the factory to see that all explosives sent out are what they are meant to be, and that they can therefore be relied upon to behave according to program and not to play any tricks. That is the first step, and what with competition between makers, government inspection, and searching inquiry into the slightest accident, and the desire of each maker to keep up the credit of his name, it is safe to say that modern explosives may be relied upon to do their duty faithfully. The second step in the process of securing safety is that the powerful explosive, the one that does the work, is made very insensitive, so that it is really quite hard to explode it. With reasonable care, then, it will never go off by accident. On the other hand, the sensitive material which is easy to let off is in very small quantities, so small that an accident with it would not, again with reasonable precautions, be a serious matter. Fuse, too, is very reliable nowadays. The man who lights the fuse may be absolutely sure that he will have that time to get to a place of safety which corresponds to the length of fuse which he employs. With electrical firing, too, It is quite easy to arrange that the final electrical connection shall not be made until all are at a safe distance, so that a premature explosion is impossible. In many of the cases described, the shock takes place almost entirely within the earth, and there is very little debris thrown about. Indeed, the only danger which is to be feared with these operations is about on a par with that which every farmhand runs from the kick of a horse. Any careful, trustworthy man could be quite safely taught to do this work, and with the assistance of a laborer he could do all that is necessary. Given a fair amount of intelligence, too, he would take but little teaching. Altogether, there is no doubt that the use of explosives is going to have a marked effect upon farming operations in the near future. End of chapter 1.
Section 2 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. Corbin. Measuring Electricity. There are many people whose acquaintance with electricity consists mainly in paying the electric light bill. To such, the instruments whereby electricity is measured will make a specially interesting appeal. Current is sold in Great Britain at so much per Board of Trade unit. To state what that is needs a preliminary explanation of the other units employed in connection with electric currents. The public electricity supply in any district is announced to be so many volts. It may be 100, 200, or perhaps 230, but whatever it be, it is always so many volts. Then the electrician speaks lightly of numbers of amperes. He may even talk of the number of watts used by the lamps, while occasionally the word ohm will leak out. Among these terms, the general reader is apt to become completely fog-bound. But really they are quite simple if once understood, and, as we shall see in a moment, there are some very remarkable instruments for measuring them, some of which exhibit a delicacy truly astonishing. It is well at the outset to try and divest ourselves of the idea that there is anything mysterious or occult about electricity. It is quite true that there are many things about it very little understood even by the most learned, but for ordinary practical purposes it may be regarded as a fluid, which flows along a wire just as water flows along a pipe. The wire is, electrically speaking, a hole through the air, or other non-conducting substance with which it is surrounded, a water pipe being a hole through a bar of iron. So the copper core of an electrical wire is, so far as the current is concerned, but a hole through the center of a tube of silk, cotton, rubber, or whatever it be. Electricity can flow through certain solids just as water can flow through empty space. Water will not flow through a pipe unless a pressure be applied to it somewhere. In a pipe, the ends of which are at the same level, water will lie inert and motionless. Lower one end, however, and the pressure produced by gravity, in other words, the weight of the water, will cause it to move. In like manner, pressure produced by the action of a pump will make water flow. On the other hand, when it moves, it encounters resistance through the water rubbing against the walls of the pipe. Similarly, an electrical pressure is necessary before a current of electricity will flow, and every conductor offers more or less resistance to the flow of current, thus opposing the action of the pressure. Before current will flow through your domestic glow lamps and cause them to give light, there must be a pressure at work, and that pressure is described as so many volts. A battery is really a little automatic electrical pump for producing an electrical pressure, and the volt, which is a legal measure just as much as a pound or a yard, is a certain fraction of the pressure produced by a certain battery known as Clark's cell. It is not necessary here to say exactly what that fraction is, but it will give a general idea to state that the ordinary Leclanche or dry cell, such as is used for electric bells, produces a pressure of about 1½ volts. Thus we see the volt is the electrical counterpart of the term pound per square inch, which is used in the case of water pressure. A flow of water is measured in gallons per minute. An electrical current is measured in coulombs per second. Thus the coulomb is the electrical counterpart of the gallon. But in this particular, we differ slightly in our methods of talking of water and electricity. Gallons per minute or per hour is the invariable term in the former case, but in the latter we do not speak of coulombs per second, although that is what we mean, for we have a special name for 1 coulomb per second, and that name is ampere. 1 ampere is 1 coulomb per second. 2 amperes are 2 coulombs per second, and so on. There is no recognized term to denote the resistance which a water pipe offers to the passage of water through it. But in the similar case with electricity, there is a term specially invented for the purpose, the ohm. Legally, it is the resistance of a column of mercury of a certain size and weight. A rough idea of it is given by the fact that a copper wire, 1/16 of an inch thick and 400 feet long, has a resistance of about 1 ohm. The three units, the volt, ampere, and ohm, are so related that a pressure of 1 volt acting upon a circuit with a resistance of 1 ohm will produce a current of 1 ampere. A current can do work. When it lights or heats your room or drives a tramcar, it is doing work, and the rate at which a current does work is found by multiplying together the number of volts and the number of amperes. The result is in still another unit, the watt, and 1,000 watts is a kilowatt. Finally, to crown the whole story, a kilowatt for 1 hour is a Board of Trade unit. So, for every unit which you pay for in the quarterly bill, you have had a current equal to 1,000 watts for an hour. To give a concrete example, if the pressure of your supply is 200 volts, and you take a current of 5 amperes for an hour, you will have consumed 1 BTU. Perhaps it will give added clearness to this explanation to tabulate the terms as follows. Volt equals the unit of pressure, analogous to pounds per square inch in the case of water. Coulomb equals the measure of quantity, analogous to the gallon. Ampere, the measure of the strength of a current, meaning 1 coulomb per second. Watt equals the unit denoting the power for work of any current. It is the result of multiplying together volts and amperes. Kilowatt is 1,000 watts, and a Board of Trade unit, a current of 1 kilowatt flowing for 1 hour. In practice, the measurements are generally made by means of the connection between electricity and magnetism. A current of electricity is a magnet. Whenever a current is flowing, it is surrounded by a region in which magnetism can be felt. This region is called the magnetic field, and the strength of the field varies with the strength, that is, the number of amperes in the current. If a wire carrying a current be wound up into a coil, it is evident that the magnetic field will be more intense than if the wire be straight, for it will be concentrated into a smaller area. Iron, with its peculiar magnetic properties, if placed in a magnetic field, seems to draw the magnetic forces towards itself, and consequently, if the wire be wound round a core of iron, the magnetism, due to the current, will be largely concentrated at the ends of the core. But the main principle remains: in any given magnet, the magnetic power exhibited will be in proportion to the current flowing. The switchboard at a generating station is always supplied with instruments called ammeters, an abbreviation for ampere meter, for the purpose of measuring the current passing out from the dynamos. Each of these consists of a coil of wire through which the current passes. In some there is a piece of iron nearby, which is attracted more or less as the current varies, the iron being pulled back by a spring, and its movement against the tension of the spring being indicated by a pointer on a dial. In others, the coil itself is free to swing in the neighborhood of a powerful steel magnet. The interaction between the electromagnet or coil and the permanent magnet being such that they approach each other or recede from each other as the current varies. A pointer on a dial records the movements as before. In yet another kind, the permanent magnet gives way to a second coil, the current passing through both in succession, the result being very much the same, the two coils attracting each other more or less according to the current. Another kind of ammeter, known as a thermoammeter, works on quite a different principle. It consists of a piece of fine platinum wire which is arranged as a shunt, that is to say, a certain small but definite proportion of the current to be measured passes through it. Now, being fine, the current has considerable difficulty in forcing its way through this wire, and the energy so expended becomes turned into heat in the wire. It is indeed a mild form of what we see in the filament of an incandescent lamp, where the energy expended in forcing the current through makes the filament white hot. The same principle is at work when we rub out a pencil mark with India rubber, whereby the rubber becomes heated, as most of us have observed. The wire then is heated by the current passing through it, and accordingly expands. The amount of expansion forming an indication of the current passing. The elongation of the wire is made to turn a pointer. A simple modification makes any of these instruments into a voltmeter. This instrument is intended to measure the force or pressure in the current as it leaves the dynamo. A short branch circuit is constructed, leading from the positive wire near the dynamo to the negative wire or to the earth, where the pressure is zero. In this circuit is placed the instrument, together with a coil made of a very long length of fine wire, so that it has a very great resistance. Very little current will flow through the branch circuit because of the high resistance of the coil, but what there is will be in exact proportion to the pressure. The voltmeter is therefore the same as the ammeter, except that its dial is marked for volts instead of for amperes, and it has to be provided with the resistance coil. Instruments of the ammeter type can also be used as ohmmeters. In this case, what is wanted is to test the resistance of a circuit, and it is done by applying a battery, the voltage of which is known, and seeing how much current flows. All the voltmeters and ohmmeters mentioned owe their method of working to what is known as Ohm's law. One of the greatest steps in the development of electrical science was taken when Dr. Ohm put forward the law which he had discovered, whereby pressure, current, and resistance are related. The reader will probably have noticed from what has already been said about the units of measurement, the volt, the ampere, and the ohm, that the current varies directly as the pressure and inversely as the resistance. That is the famous and important Ohm's law, and anyone who has once grasped that has gone a long way towards understanding many of the principal phenomena of electric currents. But the instruments so far referred to are of the big, clumsy type, suitable for measuring large currents and great pressures. They are like the great railway weighbridges, which weigh a whole truckload at a time, and are good enough if they are true to a quarter of a hundredweight. The instruments about to be described are more comparable with the delicate balance of the chemist, which can detect the added weight when a pencil mark is made upon a piece of paper. Indeed, beside them such a balance is quite crude and clumsy. They may be said to be the most delicate measuring instruments in existence. We will commence with the galvanometer. The simplest form of this is a needle like that of a mariner's compass, very delicately suspended by a thin fiber in the neighborhood of a coil of wire. The magnetic field produced by the current flowing in the wire tends to turn the needle, which movement is resisted by its natural tendency to point north and south. Thus the current only turns the needle a certain distance, which distance will be in proportion to its strength. The deflection of the needle, therefore, gives us a measure of the strength of the current. But such an instrument is not delicate enough for the most refined experiments, and the improved form generally used is due to that prince of inventors, the late Lord Kelvin. He originally devised it. It is interesting to note, not for laboratory experiments, but for practical use as a telegraph instrument in connection with the early Atlantic cables. Before describing it, it may sharpen the reader's interest to mention a wonderful experiment which was made by Varley, the famous electrician, on the first successful Atlantic cable. He formed a minute battery of a brass gun cap with a scrap of zinc and a single drop of acidulated water. This he connected up to the cable. Probably there is not one reader of this book but would have thought, if he had been present, that the man was mad. What conceivable good can come of connecting such a feeble source of electrical pressure to the 2,000 miles of wire spanning the great ocean? The very idea seems fantastic in the extreme. Yet that tiny battery was able to make its power felt even over that great distance, for the Thomson mirror galvanometer was there to detect it. 2,000 miles away, the galvanometer felt and was operated by the force generated in a battery about the size of one of the capital letters on this page. This wonderful instrument consisted of a magnet made of a small fragment of watch spring, suspended in a horizontal position by means of a thread of fine silk close to the coil of fine wire. When current flowed through the coil, the magnetic field caused the watch spring magnet to swing around, but when the current ceased, the untwisting of the silk brought it back to its original position again. So far it seems to differ very little from the ordinary galvanometer previously mentioned, but the stroke of genius was in the method of reading it. With a small current, the movement of the magnet was too small to be observed by the unaided eye. So it was attached to a minute mirror made of one of those little circles of glass used for covering microscope slides, silvered on the back. The magnet was cemented to the back of this, yet both were so small that together their weight was supported by a single thread of cocoon silk. Light from a lamp was made to fall upon this mirror, thereby throwing a spot of light upon a distant screen. Thus the slightest movement of the magnet was magnified into a considerable movement of the spot of light. The beam of light from the mirror to the screen became, in fact, a long lever or pointer without weight and without friction. The task of watching the rocking to and fro of the spot of light was found to be too nerve-wracking for the telegraph operators, and so Lord Kelvin improved upon his galvanometer in two ways. He first of all managed to give it greater turning power, so that, activated by the same current, the new instrument would work much more strongly than the older one. Then he utilized this added power to move a pen, whereby the signals were recorded automatically on a piece of paper. The new instrument is known as the siphon recorder. The added power was obtained by turning the instrument inside out, as it were, making the coil the moving part and the permanent magnet the fixed part. This enabled him to employ a very powerful permanent magnet in place of the minute one made of watch spring. The interaction of the two magnets is the result of their combined strength, and that of the coil being limited by the strength of the minute current. The only way to increase the combined power of the two was to substitute a large powerful magnet for the small magnetized watch spring. This large magnet would of course have been too heavy to swing easily, therefore the positions had to be reversed. So now we have two types of galvanometer, both due originally to the invention of Lord Kelvin. For some purposes, the Thomson type, his name was Thomson before he became Lord Kelvin, are still used, but in a slightly elaborated form. Its sensitiveness is such that a current of a thousandth of a microampere will move the spot of light appreciably, and when one comes to consider that a microampere is a millionth part of an ampere, this is perfectly astounding. But there is a more wonderful story still to come of an instrument which can detect a millionth of a microampere, or 1/1,000,000th of a millionth of an ampere. It is not generally known that we are all possessors of an electric generator in the form of the human heart, but it is so, and Professor Einthoven of Leyden, wishing to investigate these currents from the heart, found himself in need of a galvanometer exceeding in sensitiveness anything then known. Even the tiny needles or coils with their minute mirrors have some weight, and so possess in an appreciable degree the property of inertia, in virtue of which they are loath to start movement, and having started are reluctant to stop. This inertia, it is easy to see, militates against the accurate recording of rapid variations in minute currents, so the energetic professor set about devising a new galvanometer which should answer his purpose. This is known as the string galvanometer. The main body of the instrument is a large powerful electromagnet, in shape like a large pair of jaws nearly shut. Energized by a strong current, this magnet produces an exceedingly strong magnetic field in the small space between the teeth, as it were. In this space there is stretched a fine thread of quartz, which is almost perfectly elastic. It is a non-conductor, however, so it is covered with a fine coating of silver. Silver wire is sometimes used, but no way has yet been found of drawing any metallic wire so thin as the quartz fiber, which is sometimes as thin as 2/1000ths of a millimeter, or about a 12/1000th of an inch. 100 pages of this book make up a thickness of about an inch, so that one leaf is about a 50th of an inch. Consequently, the fiber in question could be multiplied 240 times before it became as stout as the paper on which these words are printed. The current to be measured is passed through the stretched fiber, and the interaction of the magnetic field by which the fiber is then surrounded with the magnetic field in which it is immersed causes it to be deflected to one side. Of course, the deflection is exceedingly small in amount, and as it is undesirable to hamper its movements by the weight of a mirror, no matter how small, Some other means of reading the instrument have to be devised. This is a microscope, which is fixed to one of the jaws, through a fine hole in which the movements of the fiber can be viewed. Or what is often better still, a picture of the wire can be projected through the microscope onto a screen, or onto a moving photographic plate or strip of photographic paper. In the latter case, a permanent record is made of the changes in the flowing current. An electric picture can thus be made of the working of a man's heart. He holds in his hands two metal handles, or is in some other way connected to the two ends of the fiber by wires, just as the handles of a shocking coil are connected to the ends of the coil. The faint currents caused by the beating of his heart are thus set down in the form of a wavy line. Such a diagram is called a cardiogram, and it seems that each of us has a particular form of a cardiogram peculiar to himself, so that a man could almost be recognized and distinguished from his fellows by the electrical action of his heart. The galvanometer has a near relative, the electrometer, the astounding delicacy of which renders it equally interesting. It is particularly valuable in certain important investigations as to the nature and construction of atoms. The galvanometer, it will be remembered, measures minute currents. The electrometer measures minute pressures, particularly those of small electrically charged bodies. Every conductor, and all things are conductors more or less, can be given a charge of electricity. Any insulated wire, for example, if connected to a battery, will become charged. Current will flow into it and there remain stationary. And there is what we mean by a charge as opposed to a current. Air compressed into a closed vessel is a charge. Air, however compressed, flowing along a pipe would be better described as a current. Imagine one of those cylinders used for the conveyance of gas under pressure, and suppose that we desire to find the pressure of the gas with which it is charged. We connect a pressure gauge to it and see what the finger of the gauge has to say. What happens is that gas from the cylinder flows into the little vessel which constitutes the gauge, and there records its own pressure. And just the same applies with electrometers. Precisely as the pressure gauge measures the pressure of air or gas in some vessel, so the electrometer measures the electrical pressure in a charged body. Further, some of the charged bodies with which the student of physics is much concerned are far smaller than can be seen with the most powerful microscope. How wonderfully minute and delicate, therefore, must be the instrument which can be influenced by the tiny charge which so small a body can carry. It will be interesting here to describe an experiment performed with an electrometer by Professor Rutherford, by which he determined how many molecules there are in a centimeter of gas, a number very important to know, but very difficult to ascertain, since molecules are too small to be seen. This number, by the way, is known to science as Avogadro's constant. Everyone has heard of radium, and knows that it is in a state which can best be described as a long drawn-out explosion. It is always shooting off tiny particles. Night and day, year in and year out, it is firing off these exceedingly minute projectiles, of which there are two kinds, one of which appears to be an atom of helium. Some years ago, when radium was being much talked about, and the names of Monsieur and Madame Curie were in everyone's mouth, little toys were sold, the invention, I believe, of Sir William Crookes, called spinthariscopes. Each of these consisted of a short brass tube with a small lens in one end. Looking through the lens in a dark room, one could see little splashes of light on the walls of the tube. Those splashes were caused by a tiny speck of radium in the middle of the tube, the helium atoms from which, by bombarding the inner surface of the tube, produced the sparks. Now, if we can count those splashes, we can tell how many atoms of helium are being given off per minute. And if then we reckon how many minutes it takes to accumulate a cubic centimeter of helium, we can easily reckon how many atoms go to the cubic centimeter. But the difficulty is to count them. So the learned professor called in the aid of the electrometer. He could not count all the atoms shot off, so he put the piece of radium at one end of a tube and an electrometer at the other. Every now and then an atom shot right through the tube and out at the farther end. And since each of these atoms from radium is charged with electricity, each, as it emerged, operated the electrometer. By simply watching the twitching of the instrument, therefore, it was possible to count how many atoms shot through the tube. One atom, one twitch. And from the size and position of the tube, it was possible to reckon what portion of the whole number shot off would pass that way. The result of the experiment showed that there are in a cubic centimeter of helium a number of atoms represented by 256 followed by 17 naughts. And as helium is one of the few substances in which the molecule is formed of but one atom, that is also the number of molecules. And now consider this, please. A cubic centimeter is about the size of a boy's marble. That contains the vast number of molecules just mentioned, and the electrometer was able to detect the presence of those one at a time. Need one add another word as to the inconceivable delicacy of the instrument? In its simplest form, the electrometer is called the electroscope. Two strips of gold leaf are suspended by their ends under a glass or metal shade. As they hang normally, they are in close proximity. Their upper ends are, in fact, in contact and are attached to a small vertical conductor. A charge imparted to the small conductor will pass down into the leaves, and since it will charge them both, they will repel each other, so that their lower ends will swing apart. Such an instrument is very delicate, but because of the extreme thinness of the leaves, it is very difficult to read accurately the amount of their movement, and so to determine the charge which has been given to them. In a more recent improvement, therefore, only one strip of gold leaf is used, the place of the other being taken by a copper strip. The whole of the movement is thus in the single gold leaf, as the copper strip is comparatively stiff, and it is possible to arrange for the movement of this one piece of gold leaf to be measured by a microscope. The other principal kind of electrometer we owe, as we do the galvanometers, to the wonderful ingenuity of Lord Kelvin. In this, the moving part is a strip of thin aluminum, which is suspended in a horizontal position by means generally of a fine quartz fiber. Since it is necessary that this fiber should be a conductor, which quartz is not, it is electroplated with silver. Thus, a charge communicated to the upper end of the fiber, where it is attached to the case, passes down to the aluminum needle, as it is called. Now the needle is free to swing to and fro with a rotating motion between two metal plates carefully insulated. Each plate is cut into 4 quadrants, the opposite ones being electrically connected, while all are insulated from their nearest neighbors. One set of quadrants is charged positively, and one set negatively by a battery, but these charges have no effect upon the needle until it itself is charged. As soon as that occurs, however, they pull it round, and the amount of its movement indicates the amount of the charge upon the needle, and therefore the pressure existing upon the charged body to which it is connected. The direction of its movement shows, moreover, whether the charge be positive or negative. A little mirror is attached to the needle, so that its slightest motion is revealed by the movement of a spot of light, as in the case of the mirror galvanometers. Instruments such as these are called quadrant electrometers. My readers will remember, too, the string galvanometer already mentioned. The same idea has been adapted to this purpose. A fine fiber is stretched between two charged conductors, while the fiber is itself connected to the body whose charge is being measured. The charge which it derives from the body causes it to be deflected, which deflection is measured by a microscope. In all cases of transmission of electricity over long distances, for lighting or power purposes, the currents are alternating. They flow first one way and then the other, reversing perhaps 20 times a second, or it may be 200, or even more times in that short period. Some electric railways are worked with alternating current, and it is used for lighting quite as much as direct current and is equally satisfactory. In wireless telegraphy it is essential. In that case, however, the reversals may take place millions of times per second. Consequently, to distinguish the comparatively slowly changing currents of a frequency or periodicity of a few hundreds per second from these much more rapid ones, the latter are more often spoken of as electrical oscillations. And these alternating and oscillating currents need to be measured just as the direct currents do. Yet in many cases the same instruments will not answer. There has therefore grown up a class of wonderful measuring instruments specially designed for this purpose, by which not only does the station engineer know what his alternating current dynamos are doing, but the wireless operator can tell what is happening in his apparatus. The investigator can probe the subtleties of the currents which he is working with, and apparatus for all purposes can be designed and worked with a system and reason which would be impossible but for the possibility of being able to measure the behavior of the subtle current under all conditions. One trouble in connection with measuring these alternating currents is that they are very reluctant to pass through a coil. One method by which this difficulty can be overcome has been mentioned incidentally already. I refer to the heating of a wire through which current is passing. This is just the same whether the current be alternating or direct. One of the simplest instruments of this class has been appropriated by the Germans, who have named it the Rice electrical thermometer, although it was really invented nearly a century ago by Sir William Snow Harris. It consists of a glass bulb on one end of a glass tube. The current is passed through a fine wire inside this bulb, and as the wire becomes heated, it expands the air inside the bulb. This expansion moves a little globule of mercury, which lies in the tube, and which forms the pointer or indicator by which the instrument is read. As the temperature of the wire rises, the mercury is forced away from the bulb. As the temperature falls, it returns. And as the temperature is varied by the passage of the current, so the movement of the mercury is a measure of the current. Another way is to employ a rectifier. This is a conductor which has the peculiar property of allowing current to pass one way but not the other. It thus eliminates every alternate current, and changes the alternating current into a series of intermittent currents all in the same direction. Rectified current is thus hardly described by the term continuous, but still it is continuous current in the sense that the flow is always in the same direction, and so it can be measured by the ordinary continuous current instruments. The difficulty about it is that there is some doubt as to the relation between the quantity of rectified current which the galvanometer registers and the quantity of alternating current, which after all is the quantity which is really to be measured. How the rectification is accomplished will be referred to again in the chapter of wireless telegraphy. But to return to these thermal galvanometers, as those are termed which ascertain the strength of a current by the heat which it produces, the simple little contrivance of Sir William Snow Harris has more elaborate successors, of which perhaps the most interesting are those associated with the name of Mr. W. Dudell, who has made the subject largely his own. Besides their interest as wonderfully delicate measuring instruments, these have an added interest since they introduce us to another strange phenomenon in electricity. We have just noted the fact that electricity causes heat. Now we shall see the exact opposite, in which heat produces electrical pressure and current. And the feature of Mr. Duddell's instruments is the way in which these two things are combined. By a roundabout but very effective way he rectifies the current to be measured, for he first converts some of the alternating current into heat, and then converts that heat into continuous current. If two pieces of dissimilar metals be connected together by their ends, so as to form a circuit, and one of the joints be heated, an electrical pressure will be generated, which will cause a current to flow round the circuit. The direction in which it will flow will depend upon the metals employed. The amount of the pressure will also depend upon the metals used, combined with the temperature of the junctions. With any given pair of metals, however, the force, and therefore the volume of the current, will vary as the temperature. Really, it will be the difference in temperature between the hot junction and the cold junction. But if we so arrange things that the cold junction shall always remain about the same, the current which flows will vary as the temperature of the hot one. The volume of that current will therefore be a measure of the temperature. Such an arrangement is known as a thermocouple. It is becoming of great use in many manufacturing processes as a means of measuring temperatures. In the Duddell thermogalvanometers, therefore, the alternating current is first led to a heater consisting of fine platinized quartz fiber or thin metal wires. Just above the heater there hangs a thermocouple consisting of two little bars, one of bismuth and the other of antimony. These two are connected together at their lower end, where they nearly touch the heater, but their upper ends are kept a little apart, being joined, however, by a loop formed of silver strip. This arrangement will be quite clear from the accompanying sketch, and it will be observed that the loop is so shaped that the whole thing can be easily suspended by a delicate fiber, which will permit it to swing easily, like the coil in a mirror galvanometer. It is indeed a swinging coil of a galvanometer, formed with a single turn instead of the many turns usual in the ordinary instruments, and it will be noticed from the sketch that there is a mirror fixed just above the top of the loop. This coil, then, with the thermocouple at its lower extremity, is hung between the ends of a powerful magnet, much as the fiber of the Eindhoven galvanometer is situated. The alternating current to be measured comes along through the heater rises in temperature, that warms the lower end of the thermocouple. Instantly, a steady continuous current begins to circulate round the silver strip, which forms the coil, and that, acting just as the current does in the ordinary galvanometer, causes the coil to swing round more or less, which movement is indicated by the spot of light from the mirror. A current as small as 20 microamperes, or 20 millionths of an ampere, can be measured in this way. Mr. Duddell has also perfected a wonderful instrument called an oscillograph, for the strange purpose of making actual pictures of the rise and fall in volume of current in alternating circuits. To realize the almost miraculous delicacy of these wonderful instruments, we need first of all to construct a mental picture of what takes place in a circuit through which alternating current is passing. The current begins to flow. It gradually increases in volume until it reaches its maximum. Then it begins to die away until it becomes nil. Then it begins to grow in the opposite direction, increases to its maximum, and dies away once more. That cycle of events occurs over and over again at the rate, it may be hundreds of times per second. Now, for the actual efficient operation of electrical machinery working on alternating current, it is very necessary to know exactly how those changes take place. Do they occur gradually, the current growing and increasing in volume regularly and steadily, or irregularly in a jumpy manner? Engineers have a great fancy for setting out such changes in the form of diagrams, in which case the alternations are represented by a wavy line, and it is of much importance to obtain an actual diagram showing not what the changes should be according to theory, but what they really are in practice. It is then possible to see whether the wave form of the current is what it ought to be. Once again, we must turn our thoughts back to the string galvanometer. In that case, it will be remembered there is a conducting fiber passing between the ends or poles of a powerful magnet, the result of which arrangement is that as the current passes through the fiber, it is bent by the action of the magnetic forces produced around it. If the current pass one way, downwards, let us say, the fiber will be bent one way, while if it passes upwards it will be bent the opposite way. Suppose then that we have two fibers instead of one, and that we send the current up one and down the other. One will be bent inwards and the other outwards. Then suppose that we fix a little mirror to the center of the fibers, one side of it being attached to one fiber and the other to the other. As one fiber advances and the other recedes, the mirror will be turned more or less. Consequently, as the current flowing in the fibers increases or decreases or changes in direction, the mirror will be slewed around more or less in one direction or the other. The spot of light thrown by the mirror will then dance from side to side with every variation, and if it be made to fall upon a rapidly moving strip of photographic paper, a wavy line will be drawn upon the paper, which will faithfully represent the changes in the current. In its action, of course, it is not unlike an ordinary mirror galvanometer, but its special feature is in the mechanical arrangement of its parts, which enable it to move with sufficient rapidity to follow the rapidly succeeding changes which need to be investigated. It is far less sensitive than, say, a Thomson galvanometer, but the latter could not respond quickly enough for this particular purpose. End of section 2.
Section 3 of Marvels of Scientific Invention. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Marvels of Scientific Invention by Thomas W. Corbin. The Fuel of the Future. We now enter for a while the realm of organic chemistry, a branch of knowledge which is of supreme interest, since it covers the matters of which our own bodies are constructed, the foods which we eat and the beverages which we drink, besides a host of other things of great value to us. Although the old division of chemistry into inorganic and organic is still kept up as a matter of convenience, the old boundaries between the two have become largely obliterated. The distinction arose from the fact that there used to be, and are still to a very great extent, a number of highly complex substances, the composition of which is known, for they can be analyzed or taken to pieces, but which the wit of man has failed to put together. Consequently, these substances could only be obtained from organic bodies. The living trees or animals could in some mysterious way bring these combinations about, but man could not. The molecules of these substances are much more complicated than those with which the inorganic chemist deals. The important ingredient in them all is carbon, which with hydrogen, nitrogen, and oxygen almost completes the list of the simple elements of which these marvelous substances are compounded. In some cases, there appear to be hundreds of atoms in the molecule. If one takes a glance at a textbook on organic chemistry, the pages are seen to be sprinkled all over with C's and O's, N's and H's, with but an occasional symbol for some other element. Another feature of this branch, which cannot fail to strike the casual observer, is the queer names which many of the substances possess. Trimethylanilene, triphenylmethane, and mononitrophenol are a few examples which happen to occur to the memory, and they are by no means the longest or queerest sounding. Another peculiarity about these organic substances is that a number of them, each quite different from the others, can be formed of the same atoms. Certain atoms of hydrogen, sulfur, and oxygen form sulfuric acid, and under whatever conditions they combine, they never form anything else. On the other hand, there are 66 different substances, all formed of 8 of carbon, 12 of hydrogen, and 4 of oxygen. This can only mean that in such cases as the latter, the atoms have different groupings, and that when grouped in one way they form one thing, in another way some other thing, and so on. This explains the extreme difficulty which the chemist finds in building up some of these organic substances. Every now and again we are startled by some eminent man stating that the time will come when we shall be able to make living things, when the laboratory will turn out living cows and sheep, birds and insects, even man with a mind and soul of his own. Yet one cannot but feel that such men, no matter how great their authority, are simply pulling the public's leg, to use a colloquial expression, for they hopelessly fail to make many of the commonest things. In many cases, where they wish to produce an organic substance, they have to call in the aid of some living thing to do it for them, even if it be but a humble microbe. For the microbes perform wonderful feats in chemistry, far surpassing those of the most eminent men. Hence the latter very sensibly use the microbe, employ it to work for them, just set things in order, and then stand by while the microbe does the work. Thus most things can be analyzed, that's to say, taken to pieces, while many things can now be synthesized, that is to say, built up from their constituent atoms, but still a great many remain, and among them the most important, the synthesis of which completely baffles man. One of the most useful and widespread substances, for example, cellulose, is at present at least utterly beyond us. We do not even know how many atoms there are in the cellulose molecule. The molecules may, for all we know, contain thousands of atoms. Indeed, many of these organic matters have very large molecules. And even if the chemist were able to make all kinds of organic matter, he would still be as far off as ever from making living matter. Indigo used to be derived entirely from plants of that name. One of the great triumphs of the organic chemist was when he produced artificial or synthetic indigo. But he is as far off as ever from making the indigo plant. It's claimed that synthetic rubber is exactly the same as natural rubber, although some users say it's not quite the same. Still, if it be so, it's dead rubber, not the living part of the plant. The time, then, is infinitely far distant when the chemist will be able to make anything with the characteristics of life, namely, to grow by accretion from, within, and to reproduce its kind. The most wonderful product of the laboratory is dead. At most, it simply resembles something which once was alive. But that's somewhat of digression. This dissertation on organic chemistry was simply intended to lead up to the question of liquid fuels, all of which are organic. In the life of today, one of the most important things is petroleum. This is a kind of liquid coal. Just how it was formed down in the depth of the earth is not clear. One idea is that it's due to the decomposition of animal and vegetable matter. Another is that certain volcanic rocks, which are known to contain carbide of iron, might, under the influence of steam, have in bygone ages given off petroleum or paraffin, to use the other name for the same thing. In many parts of the world, these deposits of oil are obtained by sinking wells and pumping up the oil. In others, the liquid gushes out without the necessity of pumping at all. This is believed to be due to the fact that water pressure is at work. Artesian wells, from which the water rushes of its own accord, are quite familiar, and are due to the fact that some underground reservoir tapped by the well is fed through natural pipes, really fissures in the rock, from some point higher than the mouth of the well. Now, supposing that a reservoir of oil were also in communication with the upper world in the same way, the descending water would go to the bottom, underneath the lighter oil, and would thus lift it up so that on being tapped, the oil would rush out. Another source of mineral oil is shale, such as is to be found in vast deposits in the southeast of Scotland. This shale is mined much as coal is. It's then heated in retorts as coal is heated at the gas works, and the vapor which is given off, on being condensed, forms a liquid like crude petroleum. In all these cases, the original oil is a mixture of a great number of grades, differing from each other in various ways. They are all hydrocarbons, which means compounds of carbon and hydrogen, and they extend from cymogen, the molecules of which contain 4 atoms of carbon and 10 of hydrogen, to paraffin wax, which has somewhere about 32 of carbon to 66 of hydrogen. For practical purposes, their most important difference is the temperature at which they boil or turn quickly into vapor. This forms the means by which they are sorted out. In a huge still, like a steam boiler, the crude or mixed oil is gradually heated, and the gas given off is led to a cooling vessel, where it's chilled back into liquid. The lightest of all, cymogen, is given off even at the freezing point of water. That's led into one chamber and condensed there. Then, as the temperature rises to 18 degrees Celsius, rigolin is given off. That's collected and condensed in another vessel. Between 70 degrees and 120 degrees, petroleum ether and petroleum naphtha are produced, and they together constitute what is commonly called petrol. Between 120 degrees and 150 degrees, petroleum benzene rises. All the foregoing taken together constitute about 8 to 10% of the whole crude oil. Then, between 150 degrees and 300 degrees, there comes off the great bulk of the oil, nearly 80%, the kerosene or paraffin which we burn in lamps. Above 300 degrees, there is obtained another oil, which is used for lubrication, also the invaluable Vaseline, and finally, when the steel is allowed to cool, there remains a solid residuum known as paraffin wax. This process is known as fractional distillation, and it will be noticed that it consists essentially in collecting and liquefying separately those vapors which are giving off at different ranges of temperature. For our purpose in this chapter, we are mainly concerned with the petrol and the kerosene. Many efforts have been made in times gone by to use kerosene for firing the boilers of steam engines. In naval vessels, a great deal is so used at the present time, but the chief method of employing oil for generating power is to use it in an internal combustion engine. These machines have been dealt with at length in engineering of today and mechanical inventions of today, and so must be simply mentioned here. They consist of two types. In one, which is exemplified by the ordinary car or bicycle motor, the oil is gasified in a vessel called a carburetor or vaporizer and then led into the cylinder of the engine together with the necessary air to enable it to burn. At the right moment, a spark ignites the mixture, which burns suddenly, causing a sudden expansion, in other words, an explosion. Thus the power of the engine is derived from a succession of explosions. If the fuel be petrol, it vaporizes at the ordinary temperature of the engine and needs no added heat. With kerosene, however, heat has to be employed in the vaporizer to make it turn readily into a gas. The other method is employed in engines of the new diesel type, in which the cylinder of the engine, being already filled with hot air, has a jet of oil sprayed into it. The heat of the air causes it to burst into flame, causing an expansion which drives the engine. An important feature in the latter type of engine is that the oil is very completely burned, so that very heavy oils can be used, oils which, if employed in an engine of the other kind, would choke up the cylinder with soot. In other words, the range of oils which can be used in this new kind of engine is much wider than is possible in the others. The latter may be likened to a fastidious man who is very particular about his food, while the former resembles the man of hearty appetite who can eat anything. And just as a man of the latter sort is more easily provided for by the domestic authorities, so the diesel engine makes the problem of the provision of liquid fuel much simpler. For it must never be forgotten that the provision of liquid fuel for the world is by no means a simple matter, since the supply is by no means adequate. The output runs into thousands of millions of gallons, and the whole world is being searched for new fields of oil, and yet it's all swallowed up as fast as it can be produced, while the coal mines do not feel the competition. A year or so ago, the United States and Russia, between them, and they are the greatest producers, obtained 5 billion gallons of oil, seemingly an enormous quantity. But on the other hand, Great Britain alone produces over 250 million tons of coal per annum. If therefore liquid fuel is to displace coal, as some people lightly think it's going to do, the supply will have to be multiplied many times. In the amount of heat which it is capable of giving, the coal of Great Britain alone beats the oil produced by the whole world. And another thing to be borne in mind is that as the coal miner goes down to the seam and sees for himself what's there, while the oil producer simply stays at the surface and draws it up with a pump, the coal man knows far more as to how much there is still left than the oil man does. We know that the coal deposits will last for many years to come, even if the production go on increasing, whereas the oil supply may fall off in the near future instead of increasing. And in both cases, we are using up capital. Coal is not being made on the earth now, at any rate in any appreciable quantity. The stage of the earth's history favorable to the formation of coal measures has long gone by, and the same probably applies to oil. It is interesting in this connection to note that coal itself is to a certain extent, or can be at all events, a source of oil. When coal is heated in order to make it give up its gas or to turn it into coke, vapors are given off, which on cooling become coal tar, at one time regarded only as a crude sort of paint. This is now the source from which many chemical substances are obtained, varying from photographic chemicals to saccharin, a substitute for sugar. So valuable are these products that there is a brisk demand for the tar in other directions than the manufacture of oils, but oils of various kinds are also obtained from it. The first step in the operations is fractional distillation, after the manner just described for petroleum. The first fraction is coal tar naphtha, then follows carbolic oil, after that heavy or creosote oil, anthracene oil, and finally there remains in the still, on cooling, a solid residue known as coal pitch. The naphtha, on being distilled again, gives among other things benzene, from which the famous aniline dyes are made, and which is useful in many industries. Creosote is largely employed as a preservative for wood, being forced into the timber under high pressure, so that it penetrates right into it and tends to prevent rotting, no matter how wet it may be. Railway sleepers are thus treated, small truckloads of them being run into a cast iron tunnel, which is then sealed at both ends, while the creosote is forced in by powerful pumps. After such treatment, they can lie nearly buried in the damp ballast for a long time without any deterioration. These coal tar substances are all very similar to petroleum and its products, hydrocarbons, compounds of hydrogen, and carbon in various proportions. Many of them could be used for fuel. But since they are based upon the supply of coal, which is itself limited, they cannot, however they may be used, do more than stave off the evil day when the supply will be exhausted. Quite different is it with alcohol, which it seems likely may be the fuel of the future. Some people will be inclined to exclaim, "What a pity to burn it," since to many the word conveys ideas of another sort altogether. There are many nowadays, however, who, like the writer, have none but a scientific interest in it. To such whiskey, for example, is but impure alcohol, and it's without the impurities that it may become of vast use to the world, thereby possibly repaying man for some of the harm which in the past it has inflicted upon him. Alcohol, again, is a hydrocarbon. It's really more correct to speak of it in the plural as alcohols, since there is a large group of substances all of the same name. Two of these are of the greatest importance, methyl alcohol and ethyl alcohol. The former is obtained from wood, hence it's sometimes called wood spirit. Wood is strongly heated in an iron still, and the methyl alcohol is given off in the form of vapor, which, on being collected and cooled, condenses into a liquid. it's exceedingly unpleasant to the taste. If it were the only kind, there would be no consumption of alcohol as a drink. The second kind mentioned is obtained by the agency of germs or microbes, and the story of its production is so interesting as to demand a little space. We will commence with the maltster. He performs the first part of the operation, starting with ordinary barley. By the action of heat, aided by natural growth, he produces the raw material on which the brewer may work. Now barley, like all grain, is largely made up of starch, and although starch will not make alcohol, it can be turned into sugar, which will. So the task of the maltster is to commence the change of the starch in the grain into sugar. First of all, it's soaked in water and spread upon floors, and heated until it begins to sprout. There is a little part in each grain called the endosperm, which is the embryonic plant, and the starch is really the food provided by nature to nourish the growing endosperm until such time as it shall be strong enough to draw its nourishment from the soil. In order that it may not be washed away prematurely, the starch is locked up by nature in closely fastened cells, and moreover it's insoluble so that water cannot carry it away. The endosperm, however, has at its disposal certain substances known as enzymes, and it increases its store of these as it grows, one of which is able to dissolve away the walls of the cells, to unlock the treasures, as it were, while the other turns the insoluble starch into soluble matter, in which state the growing organism is able to make use of it as food. So as the grain sprouts upon the maltster's floor, this process is going on. The cells are being opened and their contents converted from starch into soluble matters. Then, when the growth has gone far enough, the grain is transferred to a kiln where it is subjected to heat, by which the growth is stopped. The living part of the grain is in fact killed. That's mainly to stop the young plant from eating up the altered starch, which it would do if allowed time, but which the brewer wants to be kept for his own use. The maltster's task is now finished, and we come to the brewer's. The first thing he does with the malt is to crush it between rolls, thereby liberating thoroughly those substances which have been formed from the starch and which he intends to turn into sugar. Having crushed it, he places it in the mesh tun, a large tank of wood or iron, in which it's mixed with water and subjected to heat. While in this vessel, the enzymes become active again and turn the soluble starch or a part of it into a kind of sugar. The liquid drawn off from the mesh tun, containing of course the sugar, is subsequently boiled. Numerous flavoring matters, including hops, are added, and then it's cooled again, ready for the final process, fermentation. This takes place in a large vat or tun and is brought about by the agency of yeast, which is added to the liquid. Now yeast is a multitude of microscopic plants, round in shape and about 1/3000th of an inch in diameter. Though so small, this little organism is really quite complicated in its structure, and within its little body there are carried on complicated chemical changes which baffle entirely the most learned chemist to imitate. Further, he has yet to find out how the little yeast plant does it. He not only cannot imitate the process, he doesn't know what the process is. These little organisms multiply mainly by the process of budding. A new one grows out of the side of each old one, rapidly reaches maturity, breaks away, and commences an independent existence. No sooner it's free than it, in turn, gives birth to another. Indeed, so great is its hurry to propagate itself that sometimes the new cell begins to throw out a bud before it has itself separated from its parent. It's therefore easy to see that yeast increases in quantity by what some call leaps and bounds, but which the mathematically minded know as geometrical progression. The particular form of sugar with which we are concerned here is known as dextroglucose. This, the yeast, splits up into alcohol and carbonic acid gas. The latter bubbles up to the surface and escapes into the air, while the alcohol becomes dissolved in the watery liquid. It is believed that the yeast performs this operation not directly, but by the production of certain enzymes, which in their turn act upon the sugar. The liquid so formed is beer, but since it's alcohol with which we are concerned and not beer, many details connected with its manufacture have been omitted. Enough has been said, however, to show that by comparatively simple processes, grain of all sorts, in fact, anything which contains starch, and such things are to be found in worldwide profusion, can be turned into alcohol. All the really intricate chemical functions are performed readily and cheaply by living organisms. All man has to do is to set up the conditions under which the organisms can work. In the process just described, only a portion of the starch in the grain is converted into sugar. Hence the percentage of alcohol in beer is comparatively small. If all the starch be converted a liquid, much stronger in alcohol is produced, and if that be distilled, so as to separate the spirit from the water with which it's mixed, there results whiskey. Brandy likewise is the spirit distilled from wine, rum from molasses, and so on. In all these familiar beverages, the essential feature is this same alcohol, of the variety known as ethyl alcohol. It will be noticed that in the making of beer, the alcohol is actually formed in water. There is a sugary water which under the action of the yeast becomes an alcoholic water, and this indicates a very useful feature about the liquid when used for industrial purposes. A tank full of petrol is extremely dangerous, so much so that the storage of petrol is hedged about by all manner of precautions. The danger is that it gives off an inflammable vapor, and that if it once begin to burn, there is particularly no possibility of putting it out. Being lighter than water, it simply glows with a layer of fire any water which may be thrown onto it. The water in such circumstances simply serves to spread the naming petrol about, and so to make matters worse. Now alcohol, with its partiality for the companionship of water, behaves quite differently. True, it also may give off an inflammable vapor, but if a quantity of it catch fire, it can be extinguished in the usual way by a fire engine. The water and alcohol immediately combine. The alcohol becomes dissolved in the water, just as sugar may do, and as soon as the percentage of water in the mixture becomes considerable, the burning stops. It may be that some readers will have discovered this fact for themselves without knowing precisely what it was. It is a common dodge with amateur photographers if they want to dry a negative, quickly to immerse it in methylated spirit. The spirit seems to take the water out of the film, and itself, drying quickly, leaves the negative in a perfectly dry condition in a few minutes. Now, after using spirit in that way, it's useless to put it in a stove or a lamp. It will not burn. Methylated spirit is alcohol, and the reason why it has such a quick drying action is that it and the water in the wet film quickly mix. After immersion, the film is wet, not with water merely, but with a mixture of a lot of spirit and a little water. Hence the speed with which it evaporates, and the non-inflammability of the mixture is due to the presence of the water. Methylated spirit only differs from the alcohol in alcoholic beverages in that something is added to make it undrinkable, owing to the craving for it, which is so widespread, and the doubtful effect which it has on certain citizens. Most states regard it as preeminently a subject for taxation, thereby on the one hand bringing in a good revenue, and on the other discouraging its too free use. But those considerations apply only to drinkable alcohol. That which is to be used for industrial purposes is not in any way a legitimate object for taxation. Hence the problem arises of making a form of alcohol which shall answer all the needs of the industries which use it, and at the same time be so repulsive to the senses that no one can possibly drink it. This result is achieved by adding some of the methyl alcohol derived from the vapor given off by wood when heated, commonly known as wood spirit. This is so unpleasant that it renders the mixture of no use for drinking, and so it can safely be freed from taxation. Unfortunately, this spirit has less heating value than petrol. That means that a given quantity of each liquid will produce more heat in the case of petrol than in the case of alcohol. Indeed, the difference is about 2 to 1. Hence an engine to give out a certain horsepower would need to have its cylinders twice as big if it were to use alcohol instead of the other fuel. There is a certain compensation, however, in the fact that alcohol is very easily compressible. In modern internal combustion engines, much of the efficiency is due to the explosive charge which is drawn into the cylinder being compressed into a small space before it's fired. It was the discovery of the value of compressing the gas which made the gas engine so formidable a rival to the steam engine, and the wonderful performances of the diesel engines are due very largely to the fact that the air is compressed in the cylinder to a very high pressure. The jet of oil burns in highly compressed air, and because of the facility with which alcohol can be compressed, it's said to be more effective as a source of motive power than would be expected from its comparatively feeble heat. Thus we may sum up the possibilities of the future. Coal, petroleum, and their derivatives exist in limited quantities in the world, and so far as we can see, the vast drafts which we are taking from them are not being replaced. Indeed, at this stage of the earth's development, cannot be replaced by any more. Sooner or later, we must come to an end of them. Is it not comforting, therefore, to know that there is another source of fuel at hand, inexhaustible, since it can be produced as needed? We have only to set the sun and the ground to work to produce grain, rice, potatoes, or any of the myriad substances which contains starch, and from that, by simple and well-known processes, we can obtain a cheap, safe, and reliable fuel. Indeed, there seems nothing but the ultimate laws of sunlight, countless millions of years hence, which can ever check the supply of this valuable commodity. What has doubtless in many cases been a curse in the past may turn out to be the great boon of the future. End of section 3.